The next speaker is Mr. Kevin Menard, and the title is Improving TruffleRuby's Startup Time with the Substrate VM.
Hi, thanks for coming out. I know we're heading into the tail end of the conference here, so yeah, thanks for coming. So my name's Kevin. I work at Oracle. In particular, I work with a team working on a new implementation of Ruby called TruffleRuby. And this is part of a larger research group that investigates and works on virtual machine and compiler technology. Before I get started, I do need to inform you that what I'm presenting today is research work out of a research group and shouldn't be construed as a product announcement. Please don't buy or sell stock in anything based on what you hear today. So yeah, improving TruffleRuby's startup time with the Substrate VM. Wish I picked a shorter title, but it's descriptive. So for those of you that aren't familiar with TruffleRuby, you're probably wondering, what is this? TruffleRuby, as I said, is an alternative implementation of Ruby. It's relatively new, although it's been around for 4 years. I think it was originally called Ruby Truffle. Then we merged with JRuby. At that time, it became JRuby plus Truffle. About a year ago, we rolled it back out into its own project, now called TruffleRuby. I like to think of TruffleRuby as kind of a Rubyist Ruby. So we still pull in a fair bit of code from JRuby. We use their parser, encoding libraries, transcoding tools, regular expression engine, as well as some utility functions. So TruffleRuby is written in Java, like JRuby. But like Rubinius, we wanted to run as much of Ruby in Ruby. So we've pulled in a lot of their core library, and we now actually implement a lot of Ruby within Ruby. And then we also pull in code from MRI, so we pull in the standard library. But recently, we've started running MRI-C extensions as well. So quick rundown on completeness. We run about 96% of the core library specs. Around this time a year ago, I think we were at 90 or 91%. So it's something we've continued to make progress on. Some of the missing functionality are things that are hard on the JVM, like forking. As the language specs go, we pass 99% of those. I think we fail 1 or 2 of them. We've been actively looking at support for various Ruby gems. Active support's really popular ones, so I reported it here. We've almost achieved 100% compatibility with that. So TruffleRuby is Ruby implemented with Truffle. So a natural follow-up question is, what's Truffle? Truffle is a language toolkit for generating simple and fast runtimes. They're simple because the idea behind Truffle is you build an AST interpreter, and then that's it. AST interpreters are about the simplest possible runtime you can build, but they have a tendency to be slow. They're very simple to reason about, very simple to debug, but they end up walking a full tree, and they're generally more efficient ways of achieving that. MRI went through this, so up through Ruby 1.8, it was a simple AST interpreter. With 1.9, they switched to a new virtual machine and the YARB instruction set. But with TruffleRuby, we want Truffle and Graal, which is our optimizing compiler, to take care of this for you. So Graal is our JIT, and Truffle knows how to communicate with that. So it optimizes runtimes using a process called partial evaluation. I don't have time to get into all that, but Tom Stewart gave a really good talk on partial evaluation for Rubyus. I don't remember which conference it was, but if you just search for it, I'm sure you'll find it. But in addition to building the AST interpreter, we want Truffle to provide common VM runtime component. So it's kind of intended to be a one-stop shop. So we provide a debugger. We have a general instrumentation API, so you can build a profiler if you'd like. We provide some of the JIT controls, so you can instruct your code to unroll loops. And if you have like black hole methods you don't want to inline, that's available. You get tools for implementing inline caches and things like that. But with Truffle, we also have this polyglot feature. So every language implemented with Truffle basically extends from the same node hierarchy for implementing the ASTs. And Truffle has a first-class feature where languages can call in and out of each other. And because they kind of all extend from a base class, we can mix and match nodes from different languages. And then when it gets time to optimize that with Graal, we can actually compile that across language into a single optimized method. So we basically have zero overhead cross-language calls. And this is a first-class feature of Truffle. Truffle actually builds some of its functionality as domain-specific languages with Truffle itself. So it helps us stay honest, and it's a really powerful feature. So if you build a language with Truffle, you can gain interoperability with TruffleRuby. We have a JavaScript implementation, an R implementation. Out in the wider community, there's Smalltalk implementations, Python, and so on. Briefly, some of the milestones we've hit in the last year. As I mentioned, TruffleRuby was part of JRuby, where we were JRuby plus Truffle. We are now our own project, and we've rolled back out. We can now run MRI-C. So we have SSL working. As of this past week, we have our first SQL query running with the MySQL gem. And we have some zlib support going. So the way we achieve this is with a LLVM bitcode interpreter called Seulong. Chris Seaton, who's on our team, gave a talk on how all this works at last year's RubyConf. So if you're interested in that, I urge you to go check out that talk. The reason we don't have 100% compatibility is the MRI-C extension API is quite vast. So we need to provide implementations for each of the RB underscore functions or the various macros. So I think we've proved that the overall approach we want to take works, but we just need to fill in these implementations. So we've been trying to prioritize the extensions we're going to work with first. We now have a Java interop capability. So this works like JRuby's. It allows you to call into Java from Ruby. And we've been working on improving our native calls with one of these Truffle DSLs I mentioned called the native. So with this, we can basically inline some functionality related to pointers and things like that. So we can make our native calls. So, but we still have kind of this core problem, and that has to do with startup time. So this is something that's come up as a bit of a theme in various other talks at this conference. But during the application lifecycle, you have three basic phases. You have startup time, which is the runtime itself needs to get itself into a state where it can start running code. You have warm-up. So when you first start running code, it tends to be slower than when you run it many times. So if you have a JIT, this would be when you start compiling things. But even if you don't have a JIT, the file system needs to populate the file system caches. You're populating CPU cache lines, things like that. So even MRI has a bit of a warm-up, as Noah demonstrated in his talk a couple days ago. And then you hit this steady state, which is everything's warmed up, your code's running, and generally that's as fast as it's going to be. So there's two basic application profiles. There's long-lived applications. And this is the type we've basically optimized for with TruffleRuby. So our startup time and our warm-up time are relatively slow, but we expect you will spend so much time in this steady state that when we generate faster code, it will pay for itself in those slower phases. But Ruby's also used in short-lived applications, and this is a bit of a problem for us. So here we can see the startup time doesn't actually get longer. It just now accounts for a greater overall percentage of the application's lifetime. So startup now takes up a much longer portion of the of the program's runtime. Then you spend some time in warm-up, that may very well all be wasted because then you hit steady state and very quickly drop out. So what are we actually looking at? So running a simple Hello World app, we can see MRI has a very strong advantage with regards to startup time. It's around 40 milliseconds. JRuby's about 1.4 seconds, and then TruffleRuby's at 1.7. So not great. Nobody actually runs Hello World in production. So, but it was meant to be illustrative. To give a more real-world example, I also looked at the Ruby spec suite. So what this is it's a set of Ruby tests that Ruby implementations run to test their compatibility with Ruby overall. And what's nice about this is basically all the Ruby implementations run it. And it breaks itself into multiple components like language features, the core library, standard library, C API, and so on. It also provides an RSpec-like test runner called mspec. So I think it's a useful proxy for what you can expect in your own tests, whether they be BDD or TDD. And it has a decent number of tests. So there's like 2,100 examples or test cases, and it runs about 3,800 expectations or assertions. And here we can see MRI also has a really nice advantage. So it's able to run that entire test suite in about 1.5 seconds. JRuby comes in about 33 seconds, and TruffleRuby's way at the end here at 47.4. So this is our problem. We need to fix that. So, what do you get for this then? So we think peak performance is a nice advantage for TruffleRuby. So to look at this, I'm using the opcaret benchmark. This is the benchmark that Ruby is now using to validate its 3x3 progress. So it's basically an NES emulator, the Nintendo Entertainment System, written in Ruby. And an interesting aspect of this is the NES hardware renders at 60 frames per second, and MRI 2.0 is about 20 frames per second. So if Ruby 3 is able to meet its 3 times objective, it'll run as fast as NES hardware. So you can see MRIs run around 23 frames per second. JRuby is pretty close to double at 46 frames per second, and TruffleRuby is at about 197 frames per second. So we're at like 8.5 times MRI there. A little bit more will be 9 times, and then we'll really be 3x3. So this presents something of a dilemma because you want to optimize for development, but also optimize for production. And I'm looking at JRuby for this because they've really been the mature alternative to MRI for quite some time now. And people using it have had to make these trade-offs. So in a lot of cases, people just decide they're going to use MRI for everything. And they'll accept that they're not going to have peak performance, but they'll have that fast startup time. And their test suites will run quickly. They'll be able to start up Rails console very fast, and so on. So they're actively choosing to optimize for developer time. The other way to go is you always run the alternative Ruby implementation. And then you get your peak performance and advantage, which is really nice for your customers. But you just have to eat that slower startup time in development. Or you can adopt a hybrid approach. And some companies have done this very successfully. Prior to Truffle, I attempted it and really couldn't make it work. It's not without risks because you're running 2 different runtimes against the same application. You can set up CI and whatnot and hope to catch those issues. But you can run into real technical hurdles with this too, particularly if you're using native extensions. And bundler gets really weird if the Ruby engine changes. So it is a workable solution, but it involves some effort to get set up. So can we do better? I'm hoping the answer is yes, otherwise the talk isn't really worth it. So I'm introducing a new project here called the Substrate VM. So TruffleRuby can already target 2 different virtual machines, essentially. It runs on the JVM, And it will run just as an AST interpreter there, and you don't get your peak performance, but it will be 100% functional. We have a separate distribution called the Graal VM, which is basically the JVM packaged with the Graal compiler, and this is where you'll see your peak performance. The Graal VM as a total distribution also includes the JavaScript and R and Seulong languages, so you get a full Truffle development environment. Starting with Java 9, you should be able to add Graal right to a standard JVM. The timing here is a bit unfortunate because Java 9 comes out in 2 days. So if it's interesting to you, you might want to check that out. But the basic idea here. So taking the same TruffleRuby code base, we can actually just change the virtual machine we're going to run it on with basically no changes to the application. So the Substrate VM is interesting. It has 2 basic components to it. It has an ahead-of-time compiler, also known as the native image generator. And what you do is you feed in your application, which in this case is TruffleRuby, as well as the JDK and any jars, which are Java's equivalent of gems. So basically all the code you need to run your application, which again in this case is the TruffleRuby interpreter. And it ahead of time compiles it. It treats Java just like as if it were C or C++ or Go. And what you get out of it is a static native binary. And it links the Substrate VM into that binary, so you still get VM components. So you still have garbage collection. You have hardware and platform abstraction, all the things you come to expect when writing for a JVM instead of trying to write directly to low-level languages. To make the point a bit clearer, here's a Java method, and left you can see what happens when you compile with the JVM. So you use a tool called Java-C, which is Java's compiler, and what you get out of it is Java bytecode. And the JVM has a bytecode interpreter. It understands how to run this, but it's not fast at this stage. If the method becomes hot, it gets jitted by the JVM, and then you'll get machine code. On the right-hand side, you can see the output from the ahead-of-time compiler with the Substrate VM, and what you're getting is real machine. So when you run the output of this image generator, you don't have a JVM at all anymore. So the way this works is that compiler basically performs a closed world static analysis on your application. It's closed world because it can only work with the classes that you've fed into the compiler. So generally the entire JDK and those jars. But this also means you can't do dynamic class loading. And what it does is it looks at the main class, the main method. So unlike in Ruby, where you can kind of just run a script file, Java works more like C, where you have a main method. And that's a static method, which is like Ruby's equivalent of class methods. So it's not to a particular object. And it basically figures out all the types that can be reached, and then it throws everything else away. So you're not compiling the entire JDK into the binary. You're only compiling the pieces you actually use. Now this analysis needs to be conservative, so if it's unable to determine the type being used because Java has interfaces and class hierarchies and things like that, then it needs to compile everything in that adheres to that interface or falls in that class hierarchy. So you do need to be a bit careful. Christian Wimmer gave a talk on this at this year's Java Language Summit called Polyglot Native. That's basically just the Substrate VM. He gets into much more detail about what this analysis really looks like. But some interesting opportunities present themselves with this. So because we load up all the classes during the compilation process, we can execute any static assignments or any static blocks. And again, this would be like just running code in a Ruby class body when you load the Ruby class. Generally, these static methods are these static blocks are executed when you load a Java class, but we're not loading Java classes at runtime. We're loading them during the build process. So we can do things like pre-build the AST and store that built AST into a static field. And then when we start up the built application, the AST is already built for us. So we can start to reduce our startup time by basically pre-building things that we know aren't going to change. So we also have our encoding tables, transcoding maps, and some common strings. There are some limitations if you're a language implementer. Again, you can't dynamically load Java classes. You need to use extra care if you're using the unsafe API. As its name suggests, it is unsafe. But the SubstrateVM class model or object model is slightly different than the JVM one. So if you're trying to calculate field offsets and things like that, they might not work the same way. So you need to take some care there. And then on these megamorphic calls, like the ones I mentioned that would kind of compile in the entire world, you can use this Java annotation called Truffle boundary to basically tell the analysis to stop looking, and then it won't compile everything in. It'll just do a basic Java dispatch to the method. All right, so what does the Substrate VM actually buy us? This is what our startup time looks like. TruffleRuby on the Substrate VM now drops from 1.7 seconds to 100 milliseconds on Hello World. So for all your production Hello World apps, we are in good shape. Taking a look at the language specs, this is what the situation looked like before. We now drop from 47 seconds to just under 10 seconds. Thank you. There's no reason we can't get down to MRI speed, I don't think. So we're actively working on this. I have an idea of how to trim another couple seconds off, but ran out of time before the conference. So what do we get for this? Did we sacrifice peak performance? Because we've kind of treated it as this trade-off between startup time and peak performance. So this is what our performance looked like before. We actually do take a little bit of a hit on the Substrate VM right now. It's about 15%, but we're still running opcarrot at 169 frames per second, which is much faster than MRI. So why the performance hit? There's a couple reasons at play here, but opcarrot runs in a very tight loop, this dynamic call. So first it splats an array, so it's constantly creating these small arrays, and then it's using a send call, which very quickly becomes megamorphic. So it blows through inline caches. If you're interested in how all that works, I gave a talk at RubyKaigi a couple years ago on how we make metaprogramming fast. But the Substrate VM doesn't optimize creation of small arrays quite like Graal does on the JVM. In that case, it can unroll the array copy and inline much better. And the Substrate VM has slightly slower method calling, so that's something we're looking to fix. But the part that accounts for most of this is the Substrate VM currently doesn't have compressed oops. So basically, compressed oops in the JVM allow you to represent object pointers in 32 bits instead of 64. So if your total heap is less than 32 gigs, you can use compressed oops, and then your object pointers into cache lines, and generally things are much faster. So that probably accounts for 10 to 12% of that 15% hit we took. So in summary, I think we've fixed TruffleRuby's startup time. There's certainly more room for improvement. Our goal is to get as fast as MRI, and we're closing in. The Substrate VM is now publicly available as part of the Graal VM. This is kind of big because we give or get something on Hacker News or Reddit or what have you. Someone asked about startup time, and then we kind of say, yeah, we got this thing over here called the Substrate VM that's magically going to fix it. And it was starting to look like vaporware, but it's out there. It works. And I think the Substrate VM helps validate our overall approach. So again, a lot of languages throughout the course of the evolution basically start with an AST interpreter and hit a performance wall, and then need to rewrite into a custom virtual machine with a bytecode interpreter or its own instruction set, what have you. With Truffle, you stay just writing your AST interpreter, and now you have the Substrate VM as another deployment target, and you get your startup time fixed for you. So there's some future work here. The Substrate VM, as I mentioned, will get compressed dupes. There's not a technical limitation there. It just hasn't been done yet. It's a much younger project than the JVM. And we'll get that improved array handling. I'm hoping both get done maybe by the end of the year. Hard to say, but it's not that far off. As for TruffleRuby, so we had our first launch with the Substrate VM in February or March, so it's been out there for about 6 months. There's still more things we can do to take advantage of pre-building things. So currently we include all of the core library, which is mostly implemented in Ruby into the image, but we could look at adding the standard library there as well. We could reduce the overhead of native calls, and this would be pretty big for us. So Java, the way we work right now is we take a Ruby string, convert it to a Java string, go through this project called JNR, which then goes through another piece of technology called JNI that allows Java to interface natively. That string might then get copied out to a native byte array and then round trip all the way back. On the Substrate VM, we don't have the JVM to deal with, so we don't need to go through JNI. We could just make libc calls directly and hopefully avoid both overhead from the indirection and from copying these objects all the way through. So that's something I'll be looking at. And then we know we still need to work on reducing memory usage. I guess I'm being a bit preemptive here because in addition to always being asked about startup time, we're asked about our memory usage. And it's something we're aware of. The Substrate VM does help with memory, but in some ways it also makes it a bit worse at times because you now need to load up this binary, which might be 120 megs or so, and it needs to load up the compiler graph. So basically, I don't have numbers for this, but on Hello World, we can get down to like 32 megs. But for the test suite, that's not sufficient. So at some point, I will provide probably a blog post or something that will do benchmarks that plot what the time looks like with different heap sizes. I got a few slides here, just if you want to, when I publish them, to help you out. So you can download the Graal VM distribution. You have to build the Ruby image yourself. This is how you do it, and then you can just run it. This is our benchmark environment, and I've linked some related talks. And this is a snapshot of some of the Graal VM team. It's actually a pretty large team. So Oracle's funded a lot of this through either full-time employees or interns or university collaborations. So I'd like to thank everyone that contributed, particularly in the TruffleRuby team. There's Chris Seaton, Peter Halupa, Duncan McGregor, Benoit Deloze, Brennan Fish, and from the Substrate team, Voyan Yavanovich was really helpful in getting the numbers for this. So basically, this is a big team effort. I'm the one presenting here today, but I certainly didn't do all this on my own. And here's my contact information. So I'm Nerve Drum. TruffleRuby is at TruffleRuby. It's open source, so you can go on GitHub and grab this, or you can just search for TruffleRuby. And yeah, that's it. Thank you.
About 10 minutes left, so you can ask some question.
Is there any build time increase building Truffle VM binaries?
So this would be equivalent to compiling MRI from source. So you're building the interpreter, and the interpreter still runs your application. So you would only build it when a new releases come out. At some point, we're hoping to ship pre-built binaries, and you wouldn't even have to do that. But there's some distribution headaches for us currently.
Thank you.
Sorry. I've been using JRuby for a long time, and I've wondering about TruffleRuby for a while. I've been following your Twitter account and some of the other Oracle people, and I was wondering whether you still have like a large to-do list for Rails to work in TruffleRuby. I mean, is there any community effort, or is there anything that we can do to help you about that?
Yeah, so we opted to go the route of running C extensions. So we kind of ended up in this no man's land because JRuby was able to get around the C extension issue by having native extensions. And there's been a ton of community work into this project called Active Record JDBC that provides basically database drivers that are Active Record compatible through Java. But all of that is really tied to the JRuby runtime. And TruffleRuby has its own runtime with its own class hierarchy, so we couldn't take advantage of that. So we needed to either work with one or the other or come up with our own extension API and then hope to get everyone to start using that. And that seemed like a big uphill battle. So our solution was to try to get C extensions working, and that's progressed pretty nicely. So we do that through this Seulong project. Basically, we take the C extensions, we compile them with Clang to LLVM bitcode, and then Seulong is a bitcode interpreter that we can use to execute that code in Graal and through TruffleRuby. But these C extensions still use all of MRI's macros and all these RB underscore functions. For those, we need to provide implementations. So the part we can compile very nicely is the stuff calling those MRI functions or macros, but we need to provide the implementations so that everything slots together nicely. And it's just a large API, so it's a matter of just getting it done. If you're looking to get involved, there's no shortage of these things to do. And I'd be happy to help you out. You can issue pull requests, file issues, what have you. Rather than try to just take the entire list and implement them one by one, we decided we would start by picking just a handful of extensions and working on them. So OpenSSL was the first one we've done. As I mentioned, Nokogiri is almost done. And a guy on our team started working on the MySQL gem. Well, the idea, we hope, is that as we knock off one gem after another, we're converging on the set of the MRI API that people actually use, and then subsequent extensions would just be faster to implement. So our biggest problem, to get back to your real question, is that we don't really run the database drivers that Rails requires. So we can run Rails without database drivers. You can use active model, but practically nobody really does that. They want to use one of the pre-built database drivers. So, yeah.
Thank you.
So now when I want to use TruffleRuby, I can either use JVM, SVM, or GraalVM, right?
Correct.
So you mentioned the dual approach. Would you still, do we still have the same problem if I use SVM in development and GraalVM because of the peak performance in production that they're not close enough and you wouldn't recommend it?
So I wouldn't recommend using it in production at all right now anyway, but yeah, so there's still a risk component to it because you'd be deploying with a different virtual machine than what you're using in development. In this case, the one you'd be deploying with is basically the JVM, and that's pretty solid at this point. But The big risk factor, I think, with developing an MRI and deploying with JRuby is that they just have different runtimes. So JRuby does extraordinarily well with MRI compatibility, but there's always these kind of edge cases. So with the hybrid approach of using like the Substrate build in development and the Graal VM build in production, you still have the same TruffleRuby runtime. It's the same code running on both virtual machines. So the differences then become differences in garbage collection, things like that. But you would probably tune those differently in development than you would in production anyway.
Makes sense. And like now that you support another VM, is that like adding overhead for you to maintain going forward?
Not so much. The SubstrateVM team has done a really good job of responding to any issues we've opened. So outside of the core limitations of the SubstrateVM, like not having dynamic class loading because there's no bytecode interpreter, they aim to be essentially indistinguishable from the JVM. Up until very recently, they didn't allow for runtime reflection, so that was another limitation, but they were able to fix that as well. So it's nice because there's a dedicated team working on that. The TruffleRuby team can focus on building the runtime and letting the SubstrateVM team deal with building the VM. In the TruffleRuby code base, we have maybe a half dozen places where we say, if running on the SubstrateVM, do this, else do that. But it's almost essentially the same code running for both.
Thank you for your presentation. I have two questions. One, the first one is not a technical question. So many people are working on this project, so this Graal Truffle project.
Mm-hmm.
So the Oracle has some purpose, or Oracle want to make some business on this? Or you only technical challenge?
So I think you might be asking a question above my pay grade, but so I work in Oracle Labs, which is a research group within Oracle. Our mandate isn't necessarily to build stuff that is immediately commercializable, but there's an expectation that Oracle will eventually see a return on investment. I think you probably don't want to look at TruffleRuby in isolation. You'd have to look at the larger team. So Graal represents a new compiler for the JVM, and having Truffle and the various Truffle languages help build out the Graal compiler. So there's a lot of different pieces to this. And yeah, I'm sure Oracle at some point expects to be able to make money somewhere. They're pretty good at doing that.
Okay. So the second question is technical one. So maybe the key idea of the boot speed up the boot time is pre-compilation, I think. So prepare the all of source code to to the native code ahead of time. No.
Sorry, what was the question?
So the key of the key idea of this performance, so boot time speed up is pre-compilation, I think.
Yeah.
So my question is how the so which source codes are compiled before? So all of Ruby code or only Truffle related code?
So basically just the Java parts. So
Mm-hmm.
we're pre-compiling the interpreter. We're able to pre-parse the core library and then
So
take
you mean
that
library is a Java library, right?
No. So
the
we
Ruby library.
implement most of the core library in Ruby.
Mhm.
So
I see.
whereas MRI implemented in C, we implement
okay.
in Ruby.
Okay.
So when you start up TruffleRuby, we need to parse those files, build the AST, start translating
Okay.
them, and so on. When we build the image, we're pre-compiling Java, but in these static blocks that get executed, we can do things like pre-parse the Ruby files constituting the core library, and then take that pre-parsed AST and just store it as a field. And then when we start up with the image, you have this, basically memory blob that is the pre-built AST, and then we don't have to spend time parsing all those Ruby files. So the part we are compiling is the Java. We are building the AST, the TruffleRuby interpreter. We're not pre-building applications, but we're essentially kind of pre-compiling Ruby by just having the AST pre-built. But that still needs to warm up and go through its process.
Okay. Okay, thank you.
It will be the last question.
Yes. So, as just like Koji says, so you pre-parse the Ruby library, right? So, if it's possible to, in the future, maybe you can pre-parse the whole application and its gems into a binary, so we can get faster, faster runtime and stop time.
Yeah, there's no technical reason that couldn't be done. Getting back to an earlier question someone asked, every time you modified a source file, you would need to go through this, like it would be like rebuilding MRI every time you just change something in your application. So you would have to figure out, what level of trade-off you really want to make there. But there's nothing in the core technology that would prohibit doing that.
Oh, cool. Because it will be very helpful in like production system to get all the advantage of reducing all these overheads. Yeah, thank you.
If you have a question, please ask him after this session. So thank you so much, Mr. Kevin.